Hello everyone, I am Chandan from Sri Venkateswara College of Engineering from BE of Branch Information Science and Engineering. In this video, let's learn about the topic NFA. Contents we are going to learn are non-deterministic finite automata NFA, definition of non-deterministic finite automata with example, the language of an NFA, equivalence of deterministic and non-deterministic finite automata, a bad case for the subset construction. Non-deterministic finite automata (NFA). Introduction. A non-deterministic finite automata (NFA) has the power to be in several states simultaneously. The ability is often expressed as an ability to guess something about its input. For instance, when the automation is used to search for certain sequence of characters, example keywords, in a long string, it is helpful to guess what we have at the beginning of those strings and use a sequence of state to do nothing but check that the string appears character by character. Definition of non-deterministic automata, finite automata. Now let us introduce the formal notation associated with non-deterministic finite automata. The difference between DFA and NFA will be pointed out as we do. And NFA is represented especially like a DFA. A equals Q sigma Q naught F, where Q is the finite set of state. Sigma is finite set of input state symbols. Q naught, a member of Q, is the start state. F, a subset of Q, is the set of final or accepting states. The transition function is a function that takes a state in Q and an input symbol in sigma as argument and returns a subset of Q. Notice that only difference between an NFA and a DFA is the type of value and the and returns a set of states in case of NFA and a single state in the case of DFA. Now let us consider an example to explain about NFA accepting all the string that ends in 01. Q0 can be either 01 or 10 or start state can be either 01 or 10, but end state should be ends with 01 as we can see in the figure. The NFA of figure 2.9 can be specified formally as Q0, Q1, Q2, 0, 1 transition function Q0, Q2, where the transition function of is given by the transition table. The transition table for NFA that accepts all the strings ending in 0, 1, as we can see in figure 2.11. Notice that the transition table can be used to specify the transition function for an NFA as well as the DFA. The only difference is that each entry in the table for NFA is a set, even if it is a singleton as one member. Also notice that when there is no transition at all from a given state or a given input symbol, the proper entry is null, the empty set. Language of an NFA. An NFA accepting a string W if it is possible to make any sequence of choices of next state while reading the character of W and go for the start state to any accepting state. The fact that other choices using the input symbol of W lead to non-accepting state or don't lead to any state at all is that the sequence of start state dies does not prevent W from being accepted by the NFA as a whole. Formally, if A equals Q sigma Q naught F is a NFA, then language LA equals W slash sigma delta Q naught W union of F equals null. That is, language LA is a set of string W in sigma star such that Q naught W contains at least one accepting language. Equivalence of deterministic or non-deterministic finite automata. Although there are many languages for which an NFA is easier to construct than a DFA, such as language of string that ends in 01, it is a surprising fact that can be described by some NFA can also be described by some DFA. Moreover, DFA in practice has about as many states as NFA, although it often has more transitions. In the worst case, however, the smallest NFA can be 2 2 to the power n states, 2 to n states, while the smallest NFA for the same language has only n states. The proof that DFA can do whatever NFA can do involves as important construction called the subset construction. Bad case for subset construction. It is quite common in practice for DFA to have roughly the same number of states as the DFA from which it is constructed. However, the exponential growth in the number of states it is possible. All the 2 to the power n in DFA states that we could construct from an n-state DFA may turn out to be accessible. The following example does not quite reach that bound, but it is understandable way to reach 2 to the power n states in smallest DFA that is equivalent to an n plus 1 state NFA.